let's say we've got a function, z is a function of x and y, but the little complication here is now x is in terms of two variables, s and t, and so is y. Y is in terms of two variables, s and t. And so let's think about this. Again, one way to kind of picture this out, because it can be cumbersome to try to figure out, well, do I have everything I need, is to use a just a little tree diagram. So let's draw the tree diagram here. So z is a function of x and y. And x and y themselves are functions of s and t. And so that's kind of the tree of these functions. All right, so let's think about what makes sense here to think as far as derivatives go. So there's two paths here to s, and there's two paths, if you will, to t. And so we can think of both the derivative of z with respect to s, and we can think of the derivative of z with respect to t. So now it turns out both of those are going to be partial derivatives. Because of that fact, like I said, they're split up in both cases. So what would I need to do to compute the partial of z with respect to x? Well, like we said in the previous example, if we just follow the paths here, so to get from z to s, I can go through two different paths. So here I would need to do the partial of z with respect to x. And then to get to this s, I need to do the partial of x with respect to s. Again, that's a partial because s is in terms of x is in terms of s and t. So I need to follow that path. Oops. So partial of z with respect to x, then the partial of x with respect to s. Then to get I can also get to s, if you will, through y, so I need to do the partial of z with respect to y, and then the partial of y with respect to s. So it's more or less the same sort of thing we were doing. There are other examples, but again, the complication is now that's not the only derivative of z we can compute here. We can also do the derivative of z with respect to t. It's going to be a partial of z with respect to t. And again, just follow the trails here, if you will. It's pretty much the same. Partial of z with respect to x, and then the partial of x with respect to t, and then partial of z with respect to y times the partial of y with respect to s. So just kind of, with respect to t. It's a good visualization of that tree diagram. All right. Now, what about this one? So let's say we've got u is a function of x, y, and z. X is a function of s, t, and v. Y is a function of s, t, and v. And z is a function of s, t, and v. So we've got three variables in all cases here. Well, yeah. u is a function of x, y, and z, but then each one of these is a function of s, t, and v. And so there's basically three partial derivatives I can think of if I go through the whole progression here, right? I can do the partial of u with respect to s. I can do the partial of u with respect to t. And then the partial of u with respect to v. So those all would be legitimate partial derivatives. Well, in this particular case, each one is, there's three paths, right? To s, I can go through x, I can go through y, I can go through s, through z. So the partial of u with respect to s would be the partial of u with respect to x. And the partial of x with respect to s. That's one path, and I could go through the y, partial of x with respect to y. There's a partial of y with respect to s. Well, it's not too bad, but then I have a third path through the z. So yeah, you add a third part to our sum here. Hopefully it makes a little sense there. Like I said, the tree diagram sometimes helps. Yeah, so three different paths, and then same thing on the rest of these. You get to t, basically the same thing, except each one of these is, the second part is with respect to t. Partial u with respect to x, partial y with respect to y, and do the partial y with respect to t, and the partial u with respect to z, and do the partial z with respect to t. So as you can see, it gets quite long quickly. So this is adding, this is just 2 layers, and we could add more layers if we wanted. But all right, let's write this one, and then I'll do an example, maybe not this one, but partial of u with respect to y, and then the partial y with respect to v. That's all the changes on these. Yeah, there's nine different terms on that one. All right. Well, I don't think this one has. Let's say we've got p equals the square root of u squared plus v squared plus w squared. And then u equals x e to y, v equals y e to the x, and w equals e to the xy. So let's find the partial of p with respect to x and the partial of p with respect to y if x is 0, y is 2. Yeah, so this one isn't quite as long as that. This one we just have p is in terms of u, v, w, but u, v, and w are just in terms of x and y. So the partial of p with respect to x, what's that going to be? Well, it's going to be the partial of p with respect to u. So, and then it looks bad, but since they're all pretty much the same here, of course we got to do our 1/2 power thing here. right, so we start with the partial p with respect to u. So partial p with respect to u, v and w are fixed, so I would just have to do the chain rule. -1/2, and then since I'm doing the partial with respect to u, that would be 2u, the inside. Now I multiply that by the partial of u with respect to x. So the partial of u with respect to x would be just e to the y. Okay? But I'm going to have to go to the x through all of these. So partial of p with respect to v, and like I said, that it looks bad, but it's very much the same here. The partial of p with respect to v, well, it's going to be the same, 1/2 u squared plus v squared plus w squared to the -1/2 times, with respect to v, so that'd be 2v. So it kind of has a repetitive nature to it there. But then I do the partial of v with respect to x, and that'd be y e to the x. Y times the x, sorry. Then I have to do the third piece, and that is go through the w to the x, so that'd be the partial of w, a partial of p with respect to w. Well, it's going to be the same, except we're doing to w, which obviously gets cancellation there. All these 2's are going to cancel. Then I got to multiply the partial of w with respect to x. Okay, well that's the hardest one. Partial of that with respect to x would be e to the xy. Then I have to do the derivative of the power, so it would be times y. So it looks kind of bad, but I don't think it will be once we get it going. Now, if x is 0, let's go ahead and finish this one off. If x is 0, y is 2 here, what happens? So we got e squared. Oh, now we've got to compute u/v/w. So in that case, we're going to have u is going to be, oh, that's nice. 0 times e squared is 0. V is y, so it'd be 2 times e to the 0, so that's 2. And then w would be e to the 0 times 2, so that's going to be 1. So, all things considered, well, this one's out of the book, so they gave us some nice values. All right, so that would be u is 0, so 0 plus 4 plus 1, so it'd be 5 -1/2. U is 0. Oh. E to the y, so that's just 0. All right, so then this would be 5 to the -1/2 times v, which is 2, times y, which is 2, times e to the x, which is 1. And then this one would be 5 to the -1/2 times w, which is 1, e to the xy, so that's e to the 0, which is 1, times y, which is 2. So 5 to the -1/2. Or 4 over the square root of 5 plus 2 times 5 to the -1/2. That's what I get. So it's 6 times 5 to the -1/2. 6 square root of 5. Not too bad there. Be the partial of p with respect to x. Not too hard, just a little long. All right, so then the partial of what p with respect to y. We we gotta go through the whole spiel again, but now we're going through these to get to the y. So the partial of p with respect to u, so that's our 1/2 u squared plus v squared plus w squared, negative 1/2. It's 2u. Then I do the partial of u with respect to y. That's just going to be x equals y. Then I would do 1/2 u squared plus v squared plus w squared, negative 1/2. Now I'm doing it with respect to v. So that's the 2v. Then I'm doing the partial of v with respect to y, which is e to the x. And then last but not least, the partial p with respect to w, so that's this one, 1/2 u squared plus v squared plus w squared, negative 1/2 times 2w, times then do the partial w with respect to y, so that'd be e to the xy, then the derivative of the power is xy, we're doing with respect to y, so it'd be x times x. So that's going to be our good news is, here, I've got a times x, which x is 0, so that's 0. I got a times x here, so that's 0. Both of these terms are just 0. This one, so we'd have the 2's cancel, so we got the 5 to the negative 1/2. The v is, what's v? 2. E to the x, that's e to the 0, so that's 1. So it's just 2 times 5 into the negative 1/2, or 2. Ta-da. So yeah, they can get long.